Okay, pre-cal students, this entire year you have taken pre-calculus, and I know that's something you obviously know. Now that's about to change, okay? In this video, we are going to start looking at some basic calculus, okay? No cheering allowed. I know you guys can't wait, but you must contain yourselves, okay? I'm sure you're really excited. Your heading today is called Preview of Calculus, Lesson 3.1. Preview of Calculus, Lesson 3.1, and be sure and include today's date right here, okay? Be sure and include today's date. Now, there will be no homework from this section, okay? I just want to talk to you guys about calculus. Please take really good notes, okay? I'm going to introduce this to you and just kind of talk to you about what calculus is used for, and then we're going to get into a little bit what limits are for and stuff like that. So here we go. Please turn your books to page 204. Okay, I want to pause a second while you do that, okay? Page 204. I'll pause a second while you do that. I think this is the first time all year we have actually read word for word from your books out loud during note-taking time, alright? However, I feel that these two sections that I want to read are really, really, really important, okay? So, go ahead and turn to page 204. I'm still waiting for you guys to do that so that you're ready to go. And please follow along as I quickly read aloud some different parts from this page. Okay, here we go. If you'll look at the top of page 204, you will see three red words, and they say, "What is calculus?" I want to read that first paragraph. Please follow along and listen to me. Calculus is the mathematics of change, velocities, and accelerations. Calculus is also the mathematics of tangent lines, slopes, areas, volumes, arc lengths, centroids, curvatures, and a variety of other concepts that have enabled scientists, engineers, and economists to model real-life situations. Okay? Now that's an important paragraph. It tells you what calculus is, what it involves, what it deals with, okay? Now, the next paragraph starts off with the words, although pre-calculus. Skip that paragraph and jump down to the four bullets. Okay, they call those little circles bullets, okay? So I want to read those four bullets, and I want you to follow along, okay? Actually, before I read those four bullets, I want to go two lines up above that where it says pre-calculus mathematics. You know what? I'm going to read that whole second paragraph after all. Here we go. Although pre-calculus mathematics, listen now, although pre-calculus deals with velocities, accelerations, tangent lines, slopes, and so on, listen, there is a fundamental difference between pre-calculus and calculus. Here it is. Pre-calculus mathematics is more static, stable, non-changing, where calculus is more dynamic. Here are some examples, okay? Listen. An object traveling at a constant velocity can be analyzed with pre-calculus mathematics, right? Okay? But to analyze the velocity of an accelerating object, there's change, okay? Its speed is not the same as changing. You need calculus. Let's go over that again. An object traveling at a constant velocity can be analyzed using pre-calculus, but an object moving at an accelerating velocity, you need calculus. Okay, bullet number 2. The slope of a line can be analyzed with pre-calculus mathematics. But if you want to analyze the slope of a curve, you need calculus. There's the change again. Think here to here. And so that's the difference. Number three, a tangent line to a circle can be analyzed with pre-calculus mathematics. But to analyze a tangent line to a general graph, you need calculus. Now, I'm not going to lie, I'm not sure exactly what they're saying there since they use the word general, but I'm assuming it means a tangent line to a circle can be analyzed because you've got the circle and the radius and all of that. And I guess they're saying to analyze a tangent line to a general graph, you would need calculus. So I'll just kind of leave that one alone. Okay, let's move on to number four. The area of a rectangle can be analyzed with pre-calculus mathematics. However, to analyze the area under a general curve, you need calculus. Like here's a coordinate plane, and here's a graph that looks like this. And if you want to find the area underneath that curve, that's really difficult to do because this line, the boundary is always changing. And so it's very difficult to do that. You would need calculus. Okay? So I feel like it's important that you students understand the difference between pre-calculus and calculus. And as we get into this a little bit, okay? All right, moving on now. The process of studying calculus is usually pre-calculus first. We've done that. Then limits. And then when they say calculus, limits are actually calculus. It's a branch of calculus. And then actually after limits, it would be derivatives and antiderivatives, which are also a part of calculus, okay? But we're going to get into limits next here. That's why we are going to study limits in the next lesson, lesson 3.2, because it goes pre-cal and then limits, okay? Let me give you two examples of how limits would help us solve two calculus type of problems, okay? So please take some really good notes on this. Now, I know you probably don't want to draw this picture, okay? But you can put in your notes, page 207. You can also turn over there, okay? Now, this graph is from page 207, okay? So what we have is we have a black curving graph here, and then we have a blue line that is tangent to the black graph right here at that point, a tangent line. Do you see it okay? Alright, now, what if I wanted you to find the equation of the blue line? Okay, now just sit back. Either you're drawing this in your notes right here, or you're putting in your notes page 207, and then you're turning in your books to page 207 so you can see a little better, okay? But what if I asked you to find the equation of the blue line? I could not do it because I need 1 point. Here's 1 point. And the slope, I don't have the slope. Or I need 2 points. 1 point here and another point here. And I don't have that. Unfortunately, I don't have the needed information to allow me to find the equation of the blue line. However, here is where limits come in. Watch this carefully. A limit, now what is a limit, by the way? Here is a limit. A limit is monitoring the change of a number as other changes are being made, okay? A limit is monitoring the change of a number as other changes are being made. So in other words, in a second, I'm going to make some changes to this graph. So those are the changes being made. And when I do that, I'm going to monitor a certain number and see how that number changes. So I change the graph, and then I see how a certain number changes. Now this is a very informal definition, and I'll explain this well later. But a limit is monitoring the change of a number as other changes are being made. Now please watch this and see how I use a limit to solve this problem, okay? This graph is also on page 207, okay? So you can make note in your notes, page 207, the other graph. You can also turn there if you want to. Look at how this helps me solve the problem, okay? Now watch this very carefully. Watch this. Now look, here's the blue line right here that I wanted to find the equation of right here, and I couldn't do it. So look what I do, students. This is so brilliant. I use the same point here, and I draw a blue line to this ordered pair here, and then I find the slope of that blue line. And then I draw another, and let's say that slope was, I don't know, I just have no idea. We'll say 1/2, okay? And then we draw the slope of another blue line from the same point going to another point a little lower. Now watch this. And let's say the slope of this is, I don't know, 1/3. I'm just making this up. And then I draw another line from this point right here to another point a little lower. And let's say that slope is 1/4. Okay? And then I draw a fourth line from this point here to this point here. And let's say that slope there is 1/5, okay? 1/5. Do you not see what I'm doing? You're like, no, Mr. Arrow, I don't. Watch. Look, guys, I found the slope of this blue line, and then this blue line, and then this blue line, and then this blue line here. I'm using a mouse, so it's really hard to draw straight lines. I apologize. I'll try to go a little slower. I found the slope of that blue line. Then I found the slope of that blue line. Then I found the slope of that blue line. Do you not see what's happening? As I draw these lines, I'm getting closer and closer to the line right here that I want to know the slope of. So the slope of this line is 1/2. I'm just making this up. Then 1/3, then 1/4, then 1/5. And then I get to another line. See how these points are getting closer and closer. This point is getting closer to this point, then this point, then this point. Then you can put a point here and draw another line and find that slope. Then put a point here, draw another line. What I'm trying to show you is this. The closer you get to the line right here that you're trying to find the slope of, because once you find the slope of this line, you can then write the equation of the line. The closer you get to this blue line, the closer the slope will become almost the slope of this line. So we had 1/2. I just made that up. Then 1/3, 1/4, 1/5. Let's say we did it again, and we got a little closer. Like 1/5 is 0.2. Then we got to 0.1, or maybe like 0.13. Then 0.129, 0.128, 0.127. So we can see we're getting closer and closer to 0.12. I just made that up, okay? So it would be a good estimation to say that slope of that line right there is maybe 0.12. Okay, I just made that up. Now, and the more lines you draw, like, watch this, guys. This is really important. Watch this. Like, if I draw a line here and split those lines, then draw a line between those two lines, the more lines I draw, and the closer and closer I get to this blue line here, the blue line right here, this blue line, the closer I get to it, then the more accurate my estimation will be using limits. Okay? Alright, so I hope that makes sense. That's a good example of what limits can do for us, okay? Here's another example of using limits to solve a problem. So please watch this very carefully. What if I asked you to find the area of the region beneath the curve of this graph, this pink shaded area right here? What if I asked you to find the area of this region that's beneath the curve, but above the x-axis? Could you do that? And notice, by the way, if you want to make note in your notes, this graph comes from page 208, okay? But could you find the area of this pink shaded area? Well, to be honest with you, it's going to be very difficult to do. Alright? It's going to be very difficult to do. Now, however, we'll look at this. Look at the next two graphs on page 208, and let's talk about these. Watch how this happens, okay? If I take this pink area and divide it up into big rectangles, okay? And then find the area of rectangle number 1, rectangle number 2, rectangle number 3, rectangle and then add all those up, I get a decent idea of what the area would be under this curve, although you can see there's some areas left, right, or I didn't get to. But if I make the rectangle smaller, now notice the area that did not get counted in the area. So I can find the area of all 8 of these rectangles, add them together. So if I can make my rectangles even smaller and then smaller, let's just pretend, guys, look, let's just pretend the area of all 4 of these rectangles was, I don't know, 8 square units. And then I split these four rectangles up into 8 rectangles. Well, that gave me a more accurate area. Now my area is 9.8 or something. And then I split all these up into rectangles. So I have 16 rectangles. That's going to make my area under the curve even more accurate, because the smaller my rectangles are, then the less of these spaces I have here where that's being left out of the area. Okay, so let's say I do this again. Split all of these up into 2 triangles, or excuse me, 2 rectangles, like this. And of course I can extend it a little higher, because now this rectangle here would go up to here and then come over. That'd be this rectangle right here. Okay, so the more we do this, the closer we get to the real area. And let's say if we did that again, we got 10.3. Okay, then we split it again and found the area of all those rectangles. Might be like 10.4, and then 10.42, 10.45. So we would assume that the area, by using limits, is approximately 10.4, 10.5. So what I'm trying to show you is, remember this definition I gave you earlier, right back here, guys? Remember this? You're monitoring the change of a number as other changes are being made. Well, in this example here, the changes being made were, we were drawing all these extra lines. The number we were monitoring was the slope. We were watching how the slope changed. Well, here, what we're changing is, we're changing the rectangles. We're going from bigger rectangles to smaller, to smaller, to smaller. And then what the number, as these changes are made, the number that we're monitoring is the what? The area. Okay? And so we can see after, if you keep splitting these rectangles over and over and find the area of each rectangle and adding them up, you're going to see pretty much a number of an area like 10.2, 10.22, 10.23, 10.2245, and it's going to keep getting closer and closer to a set number, and that would be the area of this pink shaded area here underneath the curve and above the black line. Okay, really, it's pretty cool stuff. So for chapter 3, we're going to be focusing on limits. Got it? Focusing on limits. So this video hopefully did 2 things. It gave you somewhat of an idea of what a limit is, and it showed you how limits are important and how they can be used. And also, actually something else, I hope it also showed you the difference between calculus and pre-calculus. Okay, no homework from this section. Just want to give you some notes and stuff to think about. All right, if you have any questions, don't hesitate to call or email.